The Boeing B-17G Flying Fortress, designated Serial 4-85790, is reported by the Restoration Foundation to have about 50 original flight hours, while the Foundation's own public history frames the claim more narrowly as the lowest engine hours among surviving B-17s. This numerical constraint defines the aircraft's operational history, an exceptionally low-time fortress that avoided both combat service and the post-war scrapping pipeline by becoming roadside architecture in the Pacific Northwest. The paradox is that the same display that exposed it to decades of environmental damage also helped preserve it from the fate that consumed so many other fortresses. In 1947, a civilian named Art Lacey sought to purchase a surplus military bomber to mount above his commercial property in Milwaukee, Oregon. He traveled to Altus Army Airfield in Oklahoma to procure a decommissioned airframe. Military property disposal protocols of the era were rigid. They were designed to liquidate vast quantities of surplus hardware rapidly without incurring further maintenance or storage liabilities for the War Department. Civilian purchases required direct payment and immediate extraction from the military airfield. Lacey reportedly borrowed $15,000 and bought his first surplus B-17 for about $13,750. During a poorly advised test flight, the extraction operation immediately encountered a critical mechanical failure. Lacey was an experienced single-engine pilot, but he had never flown anything with more than one engine. When the landing gear refused to extend, he executed a belly landing on the airfield, and the sliding bomber collided with a second parked B-17, damaging both aircraft. What survives in the public record is not a formal accident docket, but a remarkable disposal story repeated in later accounts. The immediate operational constraint was administrative. 2 surplus bombers were damaged on a military airfield, and the purchaser was now entangled with the War Assets Administration process. The paperwork could have stopped the whole effort, but the story took a stranger turn. According to the best-known version of the story, the War Assets Administration officer chose a practical administrative escape. He declared the damage to be wind damage, turning a destructive accident into a disposal problem rather than a prolonged fight over blame. The account then has Lacey being sold another B-17 for a sharply reduced price, reported in public sources between $1,300 and $1,500. The replacement aircraft selected was Serial 4-85790. Lacey successfully flew the replacement bomber from Oklahoma to Oregon. This transit constituted the majority of its lifetime flight hours. Upon arrival, the aircraft was partially disassembled to facilitate ground transport to the commercial site on United States Route 99E in Milwaukee. The local operational decision was to mount the heavy bomber on fixed steel pylons, turning the airframe itself into structural infrastructure for a high-volume retail environment. By elevating the aircraft above the gas station, the owners inadvertently established a preservation boundary. Hundreds of surplus aircraft were parted out or melted down in the years after the war. Serial 4-85790 bypassed that destruction not because of a known legal classification, but because it had already become privately owned roadside architecture. The operational trade-off was clear. Immediate destruction had been exchanged for decades of static exposure, with the aircraft disconnected from any aviation maintenance schedule. For decades, the external aluminum skin maintained the visual profile of an intact heavy bomber against the skyline. But the structural reality inside the unsealed airframe was entirely different. How much structural damage was occurring inside the seemingly intact bomber as it sat exposed to the elements? For 67 years, from 1947 until 2014, the bomber served as a commercial canopy, while the Pacific Northwest climate imposed a relentless cycle of precipitation, high humidity, and seasonal temperature fluctuations upon the unprotected metal. Aviation aluminum manufactured during the 1940 era prioritized immediate tensile strength and rapid wartime mass production over long-term environmental resilience. The bomber was explicitly designed for dynamic flight environments where high-altitude cold and high-speed airflow actively shed moisture. It was never engineered to endure decades of static parking in a humid coastal climate without continuous depot-level protective maintenance. A heavy bomber in flight distributes its weight across the entire wing surface through aerodynamic lift. A bomber parked on a tarmac transfers its weight downward through specifically reinforced landing gear bulkheads. This particular airframe experienced neither optimal condition. Ground crews originally mounted the fuselage onto fixed steel pylons. These rigid vertical supports concentrated the immense static load into localized sections of the lower fuselage and wing root attachments. This unnatural handling geometry stressed metal components that were simultaneously undergoing severe chemical degradation. Decades of consistent rainfall easily bypassed the aging weather seals around the cockpit perspex, the nose glazing, the dormant dorsal gun emplacements, and the unsealed bomb bay doors. Once moisture penetrated the outer aluminum skin, it pooled in the lowest structural valleys of the hollow fuselage. Moisture collected in low, poorly ventilated sections of the fuselage and wing structure instead of being cleared by routine inspection, drainage, and maintenance. This trapped moisture initiated a permanent state of atmospheric and galvanic corrosion deep within the internal structural architecture. Inside the airframe, that standing moisture acted as an electrolyte between aluminum structure, steel fasteners, and other fittings. In that galvanic couple, the more anodic material corrodes faster than it would on its own, while the more cathodic material is protected. Daily temperature cycling could compound the problem by generating internal condensation across uninsulated metal surfaces, replenishing the electrolyte layer even between rainstorms. The environmental degradation advanced steadily from the inside out. The external aluminum skin panels effectively shed external rain and maintained their visual contour. That intact contour delayed recognition of structural failure within the closed wing boxes. In the lower structure and in areas where high-strength aluminum was exposed, corrosion could advance beyond surface staining. Exfoliation corrosion attacks along grain boundaries enrolled, extruded, wrought, or forged high-strength aluminum parts, forcing layers of metal to lift, swell, and separate. Left unchecked, that process reduces structural margin and can turn a once rigid component into a weakened part that must be repaired or replaced. As the internal latitudinal stiffeners and primary bulkheads weakened, the fixed pylon geometry left the remaining structure with less reserve strength against gravity and wind loading. The large aerodynamic profile of the stationary bomber effectively functioned as a massive weather vane. High winds transferred intense twisting loads directly through the decaying wing carry through structures, focusing torsional stress against the rigid steel pylons during heavy winter storm systems. The environmental constraint was pervasive and irreversible. Engineers monitoring the site faced a complex forensic problem. They had to determine the remaining structural safety margin of a hollow tube where the most critical load-bearing nodes were completely hidden behind intact exterior skin. But weather was only half the destructive equation acting on the airframe. The wooden floorboards were reportedly replaced 7 times over the operational lifetime of the commercial site, crowds of visitors moved through the internal fuselage, turning the bomber into a high-volume roadside attraction above a large gas station and restaurant complex. That public access introduced a second category of degradation, not just weather from the outside, but wear, vandalism, and repeated human contact inside the airframe. A wartime heavy bomber was engineered with extreme weight constraints utilizing semi-monocoque construction. This design means the external skin carries much of the structural load supported by a lightweight internal web of thin aluminum ring frames and longitudinal stringers. The internal architecture was designed exclusively to support a specialized crew of exactly 10 personnel. These aviators moved carefully through the aircraft wearing soft, high-altitude flight boots, interacting only with specific reinforced crew stations. The internal volume of the fuselage is primarily empty space, featuring narrow, open catwalks and exposed flight control routing. Those conditions stood in direct contrast to a continuous flow of uncoordinated pedestrian traffic wearing heavy, hard-soled street shoes. When commercial visitors moved through the aircraft, they introduced severe and unintended dynamic load paths into the fragile airframe. The primary public walkway extended from the rear entry door through the waist gunner section across the incredibly narrow bomb bay catwalk and forward into the cockpit and nose compartments. Every time a civilian stepped off the designated reinforced center lines, their entire body weight transferred directly into the thin lower fuselage stringers and the curved outer aluminum belly skin. These lightweight structural ribs were engineered to hold the aerodynamic shape of the exterior skin, not to support the concentrated vertical point load of a human standing directly upon them. Over time, that misapplied weight deformed the lower structural supports. The continuous stream of visitors generated localized wear throughout a suspended fuselage already weakened by weather, corrosion, missing parts, and vandalism. The commercial operators attempted to mitigate the localized physical damage by repeatedly laying down new internal walking surfaces over the degraded metal. Those replacement walking surfaces maintained a temporary safe path for visitors, but they did not prove that the original substructure underneath remained sound. By the time commercial access was finally halted, the engineering team assessing the site faced a severe structural puzzle. How do you safely extract a corroded, incomplete, and historically valuable shell from its fixed steel mounts without adding new damage? A geometry limit dictated the entire extraction protocol. The aircraft possessed a massive aerodynamic footprint, featuring a wingspan of 104 feet and an empty weight of approximately 36,000 pounds. Because the inherited structural condition of the lower fuselage and wing roots was severely compromised by decades of exposure, executing a standard recovery lift was structurally prohibited. The engineering team had to design a multi-point extraction strategy that cleared the fixed pylons without buckling the center carry-through structure. In August 2014, the physical extraction phase finally commenced. The operational plan required a carefully controlled lift from the pylons and immediate handling as a fragile historic airframe, not as an ordinary display object. Logistics planners had to work around the tight perimeter of the former gas station footprint and avoid adding loads that the corroded structure could not tolerate. Public sources confirm only the broad sequence. The bomber came down from its long-time perch in 2014. The precise rigging geometry, lift points, crane count, and support hardware should remain undescribed unless supported by the recovery crew's own documentation. Once the bomber was down, the next procedural hurdle was ground transport through an urban corridor with a wingspan of more than 103 feet. The airframe required controlled disassembly on site. Crews separated the major components, including the wings and fuselage sections, reducing the aircraft to pieces that could be carried on specialized trailers without forcing the entire wingspan through the road system. In December 2014, a specialized heavy truck convoy loaded the separated fuselage and detached wing sections onto custom flatbed trailers. Careful routing kept the convoy clear of low overpasses and tight urban turns, allowing the fragile components to reach the dedicated conservation hangar at the municipal airport in Salem, Oregon. The extraction and transport phase concluded without triggering a catastrophic structural collapse of the airframe. Inside the hangar, the disassembled components exposed the full extent of the internal degradation. The engineering team now faced a rigid procedural barrier regarding the ultimate objective for the aluminum shell. Once secured inside the hangar, what standard would govern the reconstruction of its shattered framework? Inside the Oregon hangar, the engineering team faced a fundamental decision about the bomber's final operational state. They could arrest corrosion, reinforce the shell enough for static museum display, or take the exponentially harder path of returning the aircraft to active flight status. The Foundation selected the airworthy objective. This single procedural decision redefined the entire scope of the project and established a rigid compliance boundary. That boundary changed the work itself. When restoring an aircraft for flight, mechanics cannot simply cut out a crumbling section of a structural frame and rivet a cosmetic patch over the void. The work must use manufacturer data, acceptable methods, proper tools, and materials of a quality that return the aircraft to a condition at least equal to its original or properly altered condition for aerodynamic function, structural strength, vibration resistance, deterioration resistance, and other qualities affecting airworthiness. A flying heavy bomber must be physically capable of absorbing takeoff loads, turbulence, and landing stresses. To achieve that, the restoration team must fabricate, source, or restore components to an approved and structurally equivalent standard, not merely to a museum appearance standard. A major phase of this reverse engineering effort focuses on the complex internal framework between Station 3 and Station 4. In the structural geometry of this restoration, that zone houses the cockpit and top turret installation, including cockpit floor support structure, frames, longerons, latitudinal stiffeners, and related flight control and instrument panel structures. Public restoration updates show major progress in this area, with significant components already rebuilt, installed, or being fitted, rather than an untouched grid awaiting total reconstruction. To execute this complex fabrication, the restoration team relies on original Boeing manufacturing drawings, surviving original parts, sourced components, and documented warbird restoration practice. The drawings provide critical geometry and manufacturing guidance, while each inherited part forces a practical decision. Can it be restored? Must it be replaced? Can it be sourced? Or must it be fabricated in-house? Machinists must turn the archival drawings into physical templates before cutting fresh aluminum sheet metal and forming the complex compound curves with traditional metalworking tools. Every newly fabricated frame, longeron, and stringer must then prove its structural integrity and exact dimensional accuracy through rigorous quality assurance inspections before it is permanently riveted into the main airframe assembly. The primary operational trade-off for selecting this absolute standard of authenticity is an immense expenditure of time and manual labor. Fabricating a single curved bulkhead frame from a raw aluminum sheet can require hundreds of specialized man-hours. By rejecting the faster and vastly cheaper static display route, the Foundation bound themselves to a forensic-level rebuilding process. Can modern engineering disciplines successfully reverse 70 years of static decay? The current evidence inside the Oregon hangar confirms a definitive state transition for serial 4485790. The Restoration Foundation has successfully reconstructed major forward sections of the aircraft, proving that what we can verify now is a viable procedural path forward, while the exact timeline for completion remains constrained strictly by the limits of manual labor. The most visible proof of this meticulous workflow is the restored forward nose compartment. The team detached and rebuilt the nose section early in the project because it was a manageable proof of concept for the larger restoration. The degraded external skin and lower supporting structures could be evaluated in isolation, replaced where necessary, and wrapped in new aviation-grade aluminum skin. Public updates now describe that restored nose section as being integrated into the cockpit area, not as an independently certified airworthy module. With the nose restored and the cockpit structure advancing, the central fuselage and wing-related assemblies require rigid alignment support during deep structural work. These external jigs and fixtures are essential because removing corroded frames, longerons, or bulkheads can temporarily reduce the stiffness of the surviving tube. The goal is to hold the aircraft's geometry straight and true while damaged structure is removed and new or restored structure is fitted. The alignment hardware does not need to be framed as a laser-surveyed legal tripwire. Its practical purpose is to keep the fuselage, cockpit, bomb bay, and wing attachment structure close enough to factory geometry that later wing fit, aerodynamic shape, and the airworthiness path remain defensible. The defining mechanical challenge on the hangar floor is the precise integration of pristine modern metal with the surviving historical structure. The engineering team evaluates every inherited component before deciding whether it can remain in the airplane. If an original wartime bulkhead or a specific upper longeron passes modern tolerance inspections and shows zero signs of fatigue, it is carefully preserved. The team then utilizes temporary aviation fasteners to perfectly align the newly formed replacement parts against the surviving historic metal. Once alignment is verified within the jigs, technicians can begin the permanent assembly process. They drive solid shank aluminum rivets using pneumatic tools and bucking bars, physically bridging the gap between 1945 factory metal and modern hand-formed structural nodes. This deliberate hybrid reconstruction process is intended to preserve the historical identity of Boeing B-17 G105VE while moving the airframe toward the safety margins required for eventual return to flight. Inside the hangar, the restoration has shifted from rescue to controlled reconstruction. The Foundation continues to advance the structural integrity of the airframe, moving steadily toward their ultimate objective. When the final rivet is driven, will the lowest time fortress in existence finally resume the flight life it was denied in 1945?